Okay. And we could also, we didn't quite say that was unique in this space. It wasn't the ball, but then I say we can iterate. You can do that. I left that as a little exercise. So local, because this is the length of time for which we could do the contraction. And I want to make two remarks on this. The first is note that the RS, the S for which we can do this well-posedness, so S is greater than D over 2, which is also greater or equal, well, actually greater than, the critical exponent, obviously, right? Okay. So we are, okay, do I say it right? Less or equal, sorry. Never mind. Okay, so this is greater than the critical exponent. So we are in what I call last time subcritical regime. So in other words, so here is your SC, here are D over 2, and we proved local well-posedness here. But in principle, we could go all the way down here, maybe included, that's a question. Sometimes happens, sometimes doesn't happen. It's even worse in the periodic case. So there is this gap. And also, in other words, we also proved this pretty easily. And really what we used was the expression of the linear solution, the explicit expression of it, and the fact that because we are in HS, S greater than D over 2, we have an algebra, so we can estimate this nonlinearity very easily. But there is room here, so we wanted to explore the possibility of pushing the local well-posedness at least all the way here. Maybe this included or maybe not, depending on the situation. Okay, so that's the idea. So this tells us that we have to work a lot harder. Another remark that I want to make is, what about extending the existence time? Okay, this is a really important question, and very much depends whether you are in a focusing or defocusing case, low, high dimension, big, or large or small nonlinearity, and so on. But I want to give you just a little bit of an example now of what is one way of extending with a very simple example using what we know. So of course, later on, it will become harder, but just. So let's take as an example, well, it's only one of them, the case D equals 1 and lambda equals 1. So this is defocusing. Okay. So in this case, Rs has to be just greater than D over 2, which is 1/2. So in particular, if we remember where the conservation laws are, here, this is S. So here is 0, which is the conservation of the mass. Here is 1, which is the conservation, well, coming from the conservation of the Hamiltonian. I'm in the defocusing case. So in particular, I know that the HS norm, actually, for any t, H1 norm, is less or equal than a constant, which depends on the initial data. And this is for all t, as long as you can define, in fact, the H1 norm. And we would like to exploit this in order to do to go from local to global, at least in this very special case for now, defocusing dimension 1. Why I didn't take dimension 2? Because for what we know at the moment, in dimension 2, S has to be greater than 1 in order for us to have the solution. And so we miss not just the L2 norm, the mass, but we also miss the Hamiltonian. We cannot use that. So we are beyond this. So that's why I'm using just for this example, dimension 1. Okay, so in particular, what we can say is the following. From what we already proved, we can say that for any u0 in H1, there exists a unique solution on the interval time minus tt, where t it's of the order with the small constant of u0 h1 there. Okay. So now we can say the following. What could be the enemy in order to redo this? So we started here with u0. Now we are at time t. You can do also in the negative, but I'm just going to write in the positive. Now I can restart the process. My new initial data is u capital T. And how much can you go? Well, you can go of the order of now u capital T in H1. So in general, if you're not in H1, the HS norm might get a lot bigger. So the interval gets a lot smaller. And you might repeat this argument for a little while, but then you cannot move forward. But the point here is that the H1 norm is uniformly bounded. So we could as well, let me call it a star here. We can just take RT of the order of C star minus 2m. And that C star will work at each step that we do here. So by iteration, we can extend u to minus infinity. Okay? All right, so that's in H1. So then the question is, what about now assume u0 is even smoother. What can you say?
Can you make it a little whiter? Maybe have a better chalk.
I was looking for the better chalk,
Yeah,
but I'm not. There were just tiny little. There is a tiny little thing. Thank you. Yeah, trying to. Okay, so what can we say if it's even smoother? What do you expect? Should it be a global solution or not? Yes, why? You want to say why?
I don't know, well, if it's in HS where it's bigger than 1, it's in H1.
Exactly. So there is definitely it's in H1, so certainly we have a global solution in H1. What about saying that actually the solution itself for each time is in HS? How would you do that? How would you prove that we say propagation of regularity? So that's so let's start with this. So certainly, since u0 is in H1, then there exists a unique solution u, which from what we did here is L infinity. Okay, in R. Well, let me say it this way. It's more precise for all t. Okay? So certainly it's there. So what you want is to upgrade the H1 to the HS. And in order to do that, we remember that this is a solution. So it's going to be like this. And what we're going to do is we're going to apply to this our operator ds. That's basically say taking the derivative order s. Now that commutes with the look at the solution in Fourier, and you see it. So this moves here. Okay, moves over because there's a commutation. Same thing here. This moves here, like that. And now I'm not expecting to be able to prove this for all length of time for the beginning. Let me just assume that at the beginning I'm between 0 and delta in time. Then I will move forward. So then what I'm going to do is I take in L2, this is less or equal than N2. And similar thing, and you have to be a little bit more delicate than last time, but you have a delta coming from this integration, and then thank you. I'm going to actually bring it back to my office next time. I know, they're precious. And the important thing is that when you take this multiply, you apply this nonlinearity, only it acts linearly, meaning only one of them is going to have the S, and then the rest is in H1. All right, now this we know is uniformly bounded. Remember, this is less or equal than that C star to M. And this is HS.
Don't you put a T there also? Are you integrating in time?
Yes, I'm integrated. Yes, yes.
Delta times t, right?
Delta times T?
No, because what I'm doing is I'm just taking the S inside, and I do the L2 inside, and then this integral is left alone. That gives me a delta.
You want the integral to be less? I don't understand.
Take the L2 of this.
Okay, so it's delta is the length of time.
That's right. Yeah, yeah. And I did it a little bit smaller than capital. Yeah, delta is time. Is here. Yes. T is in here. Okay, good. So so then, as long as delta it's very small compared to this C star, you take this guy on the other side and you get bounded from that. Okay, is that clear? So as long as delta is much smaller than this C star to the minus m. But that's okay, because, okay, we prove this from 0 to delta, and just like before, because it's all uniform, you go to 2 delta, and so on. This is propagation of regularity. Okay, so then we're done. So the point is that when you have, you pin down the well-posed in a certain order S, or S0, let's call it, then everything above that is going to be okay. And the time interval depends only on that smaller S0. So this is propagation of regularity. Okay, so I wanted to show it now in this special example, but there is really nothing specific about this. You can do this kind of argument later on also when we have more complicated situation, except that you need to make sure that when you do your estimate, the higher order derivative appears linearly here, which is usually the case. Okay. So now we want to do this upgrade that we want from this sort of situation in which you have the algebra as a space to something more delicate. And this brings me to the Strichartz estimates. And this is going to be fun because you will see the proof of Bourgain, original proof of Bourgain, which is actually, you know, not too bad. Remarkable that somehow nobody had thought about it before 1994, I guess, something like that. And we're also going to see the proof of the Strichartz estimates so Bourgain's proof, as I mentioned last time, is for a square tori, or at least rational tori, and the other proof coming from the L2 decoupling, it's for any torus. By the way, I got distracted for a moment because apparently yesterday, if you guys check the archive, there is the proof for the Kakeya problem in 3D. So that was remarkable.
By who? By who?
By Hong and Zhao.
It's a line from blood.
Yeah. So anyway, that's this is somehow connected, the L2 decoupling, all of that stuff. So. Okay, Strichartz estimates. Is, what do you say? Yeah. Actually, the funny thing is that the way I learned about it was through Instagram, so, which mathematicians usually don't use Instagram, but that made it there.
It's better than TikTok.
I only have Instagram because my mom, who is 92, is there. My nieces put their videos with her, and that's how I get to watch it. Anyway, okay, so I'm going to first state the Strichartz estimates, and then in general, and then we're going to prove them in these two, really following the historical way they were proved. And we can do it in there are many times, so it's not too bad. Okay, so theorem. As we always do, we're going to prove first for a function which has a support on a diatic block, actually a ball of a certain radius n in Fourier world, and then we're going to use a little Pauli decomposition to put all of this together. So I'm assuming that phi n, for me, n is a parameter for now, fixed. So n is fixed. This guy has a support when you take the Fourier transform of it in a ball. For now, I'm going to take in a ball center at the origin, a radius n, in the ZD lattice. But later on, you can prove that you can actually move the ball anywhere you want, and the estimate holds as well. Okay, now there are three cases. So if Q is less than 2d plus 2 over d, by the way, I'm assuming that we are in TD and any d for now, in the statement any d. Okay, and Q greater than or equal than 2. Then, when you take the linear evolution of this phi n, and now I'm taking LQ in an interval, let me write it like this. I is a time interval. So this is where t lives, this is where x lives. Okay. This is less or equal than phi n in L2. Of course, so this is phi n is only living only in an x variable. Okay. Now, if so, there is no loss of n. This is just, when I say with a little tilde here, I mean just up to an absolute constant. It doesn't depend on anything. Maybe on q, but all right. Now, if q is equal to d plus 2 over d, then there is a first loss. N to the epsilon phi n L2, and this is for all epsilon greater than 0. So that means you just need the epsilon, which is slightly bigger than 0. If q is bigger than that, then the loss is bigger. And that power is d over 2 minus d plus 2 over pq. Sorry, here it's a little bit for all epsilon. Okay. And then in L2. Okay, those are the Strichartz estimate in TD. There are lots of remarks that I should put. Yeah.
I never remember the exponents.
Yeah, I will with the regular ones. Yes. So let me make a bunch of remarks here. Unfortunately, you had to bear with me for a little while. So the first remark is, as Sergio mentioned. So let me just give you an example. So for example, the one that I will work on, in fact, in dimension 2, you see that let's look at the equality. So when q is equal to d plus 2 over d, or what is this? This is going to be 4. So this is an L4 norm, both space and time. And the loss is n to the epsilon. And this is in T2. Okay? But if you are in R2, of course you have the L44. That's one of the admissible couples. But there is no loss of epsilon, for example.
So you're just losing
Nothing. What you can say in this case, you have, in general, actually, not even supported. So L4, first of all, two differences. One is that you don't have to restrict in a finite. I didn't say this, but I hope it's clear that I was a finite interval. You don't have to restrict to the finite interval. And also, you don't have any loss. But moreover, there is not just 4-4. That's the couple that has both Q and P the same. But you can take a different P for integrating in R and a different Q integrating in X. And those P and Q are linked in a way that's called admissible couples. I'm not going to talk about that, but it's not just 4-4. And another funny thing is that if you, instead of, well, let me write here. So plus admissible couples. So there is more than just 4-4. But if you are, let's say, in the hyperbolic space, not just dimension 2, this is just an example I'm giving. There is even more than just admissible couples. The family is even larger. So even larger family. Of Strichartz.
Results for mixed norms.
Oh, yes, there are. There are. And it's what you expect. I mean, you can combine the things together. That's one reason why, maybe I shouldn't anticipate now, but you will see. I will, because the point is that the reason why you have more of these couples is because the dispersion estimate that I did the last time, the decay. That allows you not just to integrate all over the line, but also getting more exponent than just 4-4. And so if you have a mixed manifold, you can use that dispersion in one direction, for example, whatever direction is the mixed manifold. If I understand correctly what you mean with mixed manifold. Like for a torus cross R. So
on the torus, of course, yeah.
like, for example, R cross T, or R to the N cross T to the M, or something like that.
Well, different P and Q exponents.
Ah, right. No. Okay,
but
that's
in the mixed case, right? I mean, in the torus, on the torus.
On the torus, the mixed case, I have. Have you seen the mixed? You can.
There's partial progress by like Zane Lee and other people.
Okay.
So some are known, but not all of them.
Not all of them are known, exactly. So there
There are some trivial interpolations.
Okay, those we'll just don't talk about that because those are easy to map. But making progress on that is not a simple thing. Okay.
Missing the one on n to the epsilon. Wasn't there one that's sharp without the loss of n to the epsilon?
That's right.
One that's sharp.
Right. So in the case, I will talk about that. So these ones, the ones down below here, you don't lose. Are you talking about the epsilon here, Alex?
Oh, yeah, okay. So that
Yeah. So in the actual proof coming from the corollary of the L2 decoupling, that particular case, in the corollary, there is an epsilon loss. But then Kilip and Vishan proved that in that case, you can remove the epsilon.
Because if you want to use them for a critical problem, then you
Yeah,
need
yeah.
without n to the epsilon.
Yeah, for the Q strictly greater than. But Q equals, you cannot remove, yeah. Well, it's not n to the m, it's a little log. It's a log, but it's there. Yeah. Okay, now that we did this little, so let me just say, just a little consequence. If you now use a little Pauli decomposition, you can put together all the ends here, like, you first decompose your initial data in dyadic blocks. For each one of them, you use this, then you put it back together, and you get the Strichartz that tells you the following. So let me just say, so using Lidevon Pauli theory. Okay, so Oh, well, I'm not going to rewrite the whole thing, but assume, how did I write it? U0 is such that the right-hand side is finite. You will see what I mean with that. We have the following. So if Q less than, well, that number there, I'm not going to rewrite, then STU naught in LQ is less or equal than that. And you know what you have to put here, right? I'm not going to rewrite. If Q is equal, then STU naught in LQ is less or equal than U0 in HS, S strictly greater than 0. That's the loss of epsilon. And if Q is greater than star, then ST. So here I'm not making any support assumption for U0, okay? Just that the right-hand side is okay. In HS, and now S is strictly greater than that number D over 2 minus D plus 2 over Q. Okay? Okay, so these are the Strichartz states, and now I want to prove them for you. Strictly, I think so, because you know, do you remember? I mean, in the one where there is an epsilon that's removed, but I don't know if it's in the when you localize in n or when it's.
You probably want to do a little k-square function.
Yeah, I'm not sure. I need to double check. Yeah, if equal, it's and that's important for the critical stuff. So let me just equality. I'm not sure there. I have to double check. There is a. You can check the paper of. Kilipivishan, they talk exactly about that case.
When S is 0.
Where, sorry, when, confusing here, when I have equality here, right. I'm not sure what happens. This for sure is not true, S equals 0. Okay. So let's first prove.
If Q is infinity, you would say that the solution is bounded if HS is D over 2. I doubt that that's true.
Yeah.
If Q is infinity, you would deduce that
right.
The Schrödinger is bounded if initial data are in H D over 2.
Well, if
sounds like logarithmically wrong.
But that's because the lower k-square function is fails. That's not a fault about the Strichartz system. It's because the lower k-square function is fails.
Yeah.
So you can get in some Besov space if you want.
Yeah. Okay, so I have some remarks here that, well, I'll make them later. So the estimate that I wanted to, I'm not going to do all of them, but the first one that we're going to do is the following. So the proof that I'm going to give is in the following setting. So we are in the dimension 2, and this is the square torus. But the same proof works for rational. I just don't want to worry about the 2 pi's and whatever. So rational tori, the same proof works. And what we're going to prove is this, that if I take phi n supported on a ball in a frequency space, the L4, okay, now remember that if we are in the square torus, we are also periodic with respect to time. So that's why I don't put just an interval, I just put the circle because I'm periodic there. And then, so you can write L4 type tau 3, but anyway, I prefer to write it like this. And we're going to prove that this is less or equal than n to the epsilon phi n in L2. Okay, I need to also mention that this is larger than what you really can put there. Some version of log n is really what's in there. And in fact, this is the work of Hare, a Kwok. So what they proved is really using a better estimate than the one I'm going to prove you. You will see why it's better. We can also put something better there. But anyway, using that, they were able to prove global well-posedness for S strictly greater than 0. And the reason being that if you improve your Strichartz estimates in this constant here, then you can imagine that you track this down when you do the well-posedness. Then the interval time is going to be shrinking, as I mentioned before, because the norm is getting bigger. But if you think, just as an example, if you think that the interval time shrinks like 1 over n, right? But then you sum 1/2, 1/3 plus 1/4, that series does not converge, which means that you really cover the whole time interval. So by making this smaller, as actually you can prove that you have a global solution for S greater than 0. So that's a very nice paper.
You mean global in time?
Global in time, yeah, global well-posedness for not equal 0, because there we don't even know the local well-posedness. But you are able to, even though you don't have a conservation law, you can do this expansion, improving this part here. So that's a nice thing. Okay, so that's our goal, to prove this. I need to tell you a few things that we're going to need along the way.
When you take it for pi time?
Ah, right, because I'm in a square torus. And if you look at the solution of this solution, for example, taking Fourier transform of this, let me actually write it. So remember that we know this. We computed this last time. I don't know, plus or minus, doesn't matter. We have that. And this is periodic in time, because this is purely n. Of course, if you have an irrational torus, that's not quite true. So it's almost periodic, whatever, depends how irrational it is, blah, blah, blah. But in this case, it's also periodic in time. Hence, I'm putting here, OK, I don't know what the radius is, but just to indicate that it's periodic also in T.
Whatever it is, it doesn't matter. Any time will be the same, because you just do it again.
Exactly. So, but it's just that, OK. So that's, it's just easier when I will take Fourier transform also in time now, not just in space. And will be easier if you're also periodic in time, and will make things simple. Tell you a little bit more the complication that happens when you are in the irrational. Anyway, now this was just Fourier transform in space. Now let me take Fourier transform in space-time. OK. Now I'm doing space-time, tau k. And I claim that this is delta k squared in terms of distribution, OK? All right. So this is basically all I need is this. Then the rest, well, something else you will see in a moment, but this is very good to start. So now I'm going to start with this. And I can claim that the left-hand side is nothing else than the square root of the following. Let me write it like this. So, and this is the trick. No matter what, so in order to do this kind of thing, like if you have to go take instead of 4, you have 6 or 8, or that's exactly what you do. You go back to the L2, with a product of a function. Why that? Because you want to take the Fourier transform now,
So this is
Plancherel. Say it again?
It's a bilinear estimate, in fact.
Or whatever is the number. If you have 6, it's going to be
Trilinear.
trilinear. But the point is that you always go back to L2. And then for things in between, you interpolate and so on. So that's the trick. Now, we have to take Plancherel. So we take the object that is inside L2 norm. We take Fourier transform of that. We develop, and we see what happens. OK. So now, ST, and ST, and now I'm going to take Fourier transform in space-time. So my Plancherel, I continue here. And now it's a little L2 in tau, a little L2 in k, up to constant. And let me write this down. OK, there is 1/2 all the way out. And then I'm going to take the little L2 norm in tau and z, and k in z2. And then I have the square of the convolution of these things. So I have a convolution, because this is a product, right? Here. So I have a convolution. So this is sum k equals k1 plus k2, tau equals tau 1 plus tau 2. And I told you what it is, the Fourier of that. That's tau 1 minus k1 square, tau 2 minus k2 square. And then I have the Fourier coefficient, k1, k2 square. Yes. I have 2 of them, so it's 4. Sorry. OK, so now we do the integration inside. And what you see inside, so let me just now just write that down, the absolute value square. So this is the square. So when we develop the delta function, then we get that tau is equal to k1 square plus k2 square. And then I'm just doing the absolute value square in there. And this is important. This is where, I mean, the reason why this estimates work is because you end up here with some kind of sphere or whatever. Any questions so far? OK, now let me define for you. So the tau and k are fixed outside. Let me define the set as tau k. So this is the set of k1, k2. Of course, this is going to be in Z4, such that, well, let me recall that I am in the ball. So ki is less or equal to n. And then k1 plus k2, that's from the convolution. And tau is k1 square plus k2 square. So that's my set ST. OK, so now we want to end up with some little L2 norm of these guys. So we're going to do a Cauchy-Schwarz to bring the square inside. But then I can replace this as saying that the k1, k2 is an S tau k. That's just from my definition. So when I do the Cauchy-Schwarz, this brings in the measure of the set tau k, when I put the absolute value inside, and then the sum on the set S tau k of phi n k1 square hat, and then phi n k2 square. Guys with me? And the reason why this works is because you know how large this set is. This is where the Diophantine conditions come, where, you know. So let's try to see a little bit better. So how do I measure that set as tau k? All right. I'm going to do one more reduction. So I claim that the set as the measure of this set is the same as the measure of this set, just k1 in Z2, such that tau is equal k1 square plus k minus k1 square. And I know that ki is less or equal than n. Now, in this set, capital T and K are fixed. That's outside fixed. But one thing that I know is that tau is less or equal up to constant n squared, and of course K is less or equal also n. Okay, so now tau, it's also, well, of course, is in n. So this is a Diophantine equation, if you write it down. And there is a very specific estimate of how many solutions this Diophantine equation has for fixed tau and k with these constraints. And in fact, oops, I didn't put the solution. So you can say that this is less or equal than log. I think there is some constant log n, log n, or something like that. I don't remember precisely. But the point is that this is much smaller than n to the epsilon for all epsilon, greater than 0. Another way of thinking about this is that here what you are counting is the number of lattice points on, this is a circle. So it's a circle. You can find out what the radius is. And what you're trying to figure out is how many, so here there is your lattice, the Z2. And you wanted to understand how many of these guys or lattice points are on that circle. This is Gauss' lemma. It's actually written in terms of solution of Diophantine. OK, so the point is that we know this. We go back here, so we know that this is less or equal than n to the epsilon. And that's where n to the epsilon comes, but you know that it's also smaller than that because, well, there is some log thing. Now, let's go back to where we were here. So let me we're going to take the fourth root later. Let me just write the sum. So now I'm going to do the square brackets. Whatever is inside the square brackets, this now is less or equal than n to the epsilon. And then I have the sum in k in Z2, tau in Z, and the sum in S, well, if you want k1, k2 in S tau k. And I'll take the fourth root later. OK, we won't end up with the little L2 norm of Vn on the right-hand side. So we're going to do a simple Fubini or whatever, switch the order. So this is the same. Now here I'm going to sum in K1 and K2 in C2. And of Vn K1 square Vn K2 square. But I'm left with the sum in K and tau. But they are not just K and tau. There is a constraint here. The constraint is that tau is equal to K1 square plus K2 square. and k is equal to k1 plus k2. So this clearly, once you fix k1 and k2, k is completely fixed, tau is completely fixed. So this just gives you whatever, 2 or something, right? Less or equal than a constant. And you're done. That's the end. Then take the square, the fourth root, whatever you had to do. So it's not too complicated once you know what you're doing. And you understand this now in, it becomes more complicated if you have more functions, more dimensions, and so on. But I wanted to show you just this example. Now, you say why you cannot do this if you have any torus. So this is going to be a remark. Any other question on that? Is everything clear?
And this, of course, would work also for more complicated bilinears.
And in some sense, but if you, this proof in Bourgain's paper, it's, I made it particularly simple for you, let's put it that way, but it's doable. But when you go on higher, it's more complicated. The number theory becomes, it's not so straightforward. In fact, I don't think he proved them all, right, the Strichartz?
I mean, the L4 in any dimension you can prove the same way.
Yes, but when you go to
L,
L,
if you want to go below
exactly.
L4, you don't have the Strichartz.
Yes, yes. So it's
below L4.
Yeah.
He goes below L4.
Because like the admissible line would be below L4.
yeah.
Right, so the admissible line goes up. So if you want to get the optimal one, go below L4.
But it's in higher dimensions also more complicated.
I mean, the form estimate I think is the same because you just do a slicing argument.
Okay.
Right, so like if you do the 3-dimensional counting, you can fix one of the dimensions and then just count the 2.
Yeah.
And L6 would also, I mean, the L6 is
Actually, the
Well, you have to
L6A1D
slightly
is
more
exactly the same.
Yeah,
And the
just
6
Yeah.
Anyway,
So
yeah.
if you want L6 like in high dimension, you just input like
Yes.
4 and L infinity. And I think it's optimal.
Yeah. Yeah.
But in this argument, I don't think you can ever get the scaling very
That's
low.
right.
Because you're going to lose the number of divisors of n, basically.
It did improve all of them, the first thing. Okay, so I just want to make a quick comment.
I think the log outside has to be an exponential. Otherwise,
Okay. Oh, yeah. So, absolutely. Yeah. No. Exponential. Yeah, thank you. Definitely. Thanks. No, that's the exponential. Okay. So just a remark about what was the limitation of this. So if the first thing that you have to do, if you are not, so general torus, tori. So since you are not necessarily periodic in time, you have to cut off with respect to an interval time. So let's say you take a smooth cutoff in the interval time I, and then you do this. So this is what you will look at. Let me just do the 2 dimensions so that's easier with a picture. So that's where you have to start with, because you're no longer periodic in time, so you have to cut off. Now, if you progress in the way I just did here, one big difference is that instead of counting the lattice points on your, what would be an ellipse in general, because this cutoff in time, it spreads a bit, so you have to do a neighborhood of this thing. You know whatever. And then you have to count the lattice points in here, inside and on the boundary. You can do this. There is some way of doing this. You can. There is, for example, a paper of Bompieri-Pila that tells you how many you have on quadratic curves and things like that. And you get something, but you get an n to the sigma, where sigma is a fraction. Okay? So that's what happens. So if you do the argument. So in general, you don't get the epsilon greater than 0. So in order to do the precise thing, like just have the same kind of estimate we had before, 20 years had to pass. And the theorem that I just gave you, this was maybe around 94 or something like that, more or less, I don't remember. And the full proof was done around 2014. Okay? So I'm going to write for you the theorem that, I mean, the theorem is the same. There is no changes. They're exactly the same theorem, but it comes from an L2 decoupling. By the way, I have my written lecture notes. If you guys are interested, I can just send you a scan, and I will be happy to do that. I just there are going to be typos, but the exponential was correct. So at least, all right. So the full generality of Strichartz comes from the L2 decoupling theorem. And I want to spend a few minutes at least introducing this theorem, and then prove the Strichartz as a corollary of this theorem. And actually, this theorem tells you precisely, when I wrote the Strichartz estimate, I didn't tell you, when I say I truncate on an interval, I didn't tell you how the constant on the right-hand side depends on the interval in time. And the new theorem that I will state following the L2 decoupling does. So it's very precise in that sense. OK, so what's the decoupling theorem? Well, we're going to start with, so now there is no periodicity here. Now we are in RD. So let me just write that we are in RD. OK. I have a parabola. Let me call it PD. So this is in a parabola in, let me call it C. This is in RD. Maybe I should say RD plus 1. And this is tau, which is in R. And I have a parabola here. And it's truncated in the sense, let's say, from minus a half. Let me write it this way. OK. You know what I mean. Sorry, I don't want to. So it's a truncated parabola. So let's say C equals less or equal than 1/2. And then I take a neighborhood of this parabola. It's a delta neighborhood. And then let me call, and how did I know? Let me stay consistent with my notation here. Here, delta. This is a delta neighborhood of PD. OK. Then I'm going to cut this neighborhood in small cubes. My picture is not very good. But these cubes are going to be of size delta 1/2, cross delta 1/2, cross delta. They fit inside that, OK? This cube. And let me denote them by thetas. And my notation for the collection of them, it's so p theta is collection of theta cubes. Okay. So the question is now, if you have a function in RD plus 1, such that its Fourier transform is localized in this neighborhood, and you want to take an LP norm of that function, how can you write, or how can you bound that LP norm in terms of LP norms of each piece? So that's the usual harmonic analysis thing. And the theorem tells you how you do that. I mean, what's the right way of writing it? OK, so theorem is L2 decoupling. So assume F goes from RD plus 1 into C, say, and support of the Fourier transform is inside the neighborhood of the parabola. So there. this delta neighborhood. Then, for all q greater or equal than 2 d plus 2 over d, and epsilon greater than 0. By the way, let me also assume that f is in LP. No, in LQ, sorry. Okay. We have the norm, as I mentioned, so the total norm in RD plus 1 is less or equal than, now there is a delta to the power minus d over 4 plus d plus 2 over 2q minus epsilon. Of course, these things are also reflect the scalings and all of that. So, and then here is the pieces. So this is the sum, theta, and the collection of all of these guys. Then the norm. Now, I don't think I have to say this is just the f such that its Fourier transform lives localized in the cube theta. Sorry, the cube theta.
P theta is actually the parabola, right?
Yeah, sorry. PD is the parabola, and this is the neighborhood.
Oh, it's a collection of cubes along.
And PD is the collection of cubes.
Okay.
So you take all your cubes. So here now you have LQ, RD plus 1, square and 1/2. That's the typical thing that you see. Okay, so that's the L2 decoupling. Now, as a corollary of this, and this is the one that we're going to use for the Strichartz. And I'm not going to prove how you get the corollary, but it's a corollary. So all the work is really here. And then the corollary already start telling you how it could be possible to transfer your periodic setting into something which is purely continuum. Here there is nothing periodic. This is just in RD. There is no, the only thing that suggests that it might be related to the Schrödinger equation is the parabola. But there is nothing discrete, okay, in the Fourier transform, which is the situation when you have a torus. But this corollary is the first step that tells you that maybe there is some connection with the discrete setting of Schrödinger on the torus. And this is what it says. Say, assume R is fixed and is greater or equal than delta to the minus 1. Delta is a small constant fixed at the beginning. R is a larger constant, which is greater than delta to the minus 1. Greater could be up to a constant. That's, you're allowed to do that. Now, now this lambda is a discrete set that belongs to the parabola. So this is included in the parabola, PD, discrete. And what you need to have is that what we call is and delta to the 1/2 separated. Okay, what does this mean? I'm going to say in words. So this set is discrete, so it just lives on my parabola somewhere here. But, you know, I'm not telling you how it is distributed. It could be that some points are closest, close to the cluster, or some are more dispersed. But what you need to have is that in each of these cubes that we have here, there should be a finite number. And that number is uniform for the cubes that you have. There could be 3,000, but we don't care. It just has to be a finite number. So that's what it means to be delta separated.
No, I'm confused. What do you mean you have a finite number?
Yeah, so I'm stating something. I'm telling you, I'm giving you a...
1/2 to me would mean that they are separated.
Each cube. So this is a discrete set that lives on the parabola.
Okay.
Just a bunch of points. But what you need to have for that discrete set is that inside the cube, each of these cubes here, theta, that are measured, that fits inside a box like that, there are a finite number.
Okay.
That it's uniform for all of them. So like let's say the number of points in each of the theta is less or equal than m.
In the lattice, so you have
In the
lattice,
yes.
okay.
But it doesn't have to be, see, this is not, they don't need to be in Z2. They can be, like I said, they could be all crunched up in a little near the origin and more like a, they don't need to be points of the lattice. But you cannot have infinitely many getting closer and closer to 0, say, for example, because then it's not separated.
Theta to the 1/2 separated.
OK, so this is the setting for this corollary. OK, so I'm not going to write the definition, but it was easy to say in words. OK. OK, then for any epsilon greater than 0, if BR is the ball in RD plus 1 ball, center at origin, radius R, okay, the usual ball, we have the following. The average of the integral on this ball BR of the sum C in this discrete set of AC e to the ICX to the Q. So it's an average LQ norm of whatever expression, 1 over Q. This is less or equal than delta to the minus d over 4 plus d plus 2 over 2q minus epsilon, and then AXC little L2 with respect to the delta. That's the theorem.
It's essentially the same thing as the power, but just in the discrete case.
Exactly. Now, this, there is hope now that we can use for our for the proof of our Strichartz system, which I think we're going to be able to do in the next few minutes.
For the next few years.
Few minutes? No, no. To finish this for today, I don't want to restart next time because it's kind of heavy notation. But this is what we're going to use. And we're going to have, and the thing that makes this possible, by the way, you don't see it here. It looks like just that's a dot product. But these x's are in the parabolas. OK? So this xi tells, when you do this, when you express the dot product, the last one will give you xi square times the last coordinate of the vector x. So I'm going to write it down. But it's a bit misleading because here you kind of seems that how is this connected with the Schrödinger? But it is because this xi is on this discrete, but it's sitting on the parabola itself. So, OK. So let's use this now as a corollary of the corollary. So we have the Strichartz estimate. For all tori. And the reason why you can do this for all tori is because we have a lot of freedom on how to pick these points. They can be slanted or whatever. It's not anymore the Z2 that we had before. OK, so let me, it's like before. I'm just going to accept that I wanted to emphasize that now we know on the right-hand side how it depends on the length of the interval. So let me just quickly write it. So same phi n like before, meaning this is in a ball of radius n and the Fourier and so on. Let's say I is an interval, finite interval, time. This is time. And then let me say that for all epsilon greater than 0 and q greater or equal than that famous number, this would be 4 in dimension 2, we have ST phi n LQ, and now I cross TD, and TD is any torus, so dimension D, is less or equal than n d over 2 minus d plus 2 over q plus an epsilon. And now here's the length of the torus to the q, 1 over q. And then what you expect, the L2 norm of that. So this is exactly the thing that we had before. The important thing is now we know the length of the interval, and that's the L2 norm, which is what we had before. And we're going to prove this now. Too bad that it's in this blackboard that I will cover, but you know, let's see. Hopefully 3 are going to be enough. We'll see. It's just a question of basically reducing yourself to being in the correct rectangle or whatever, cube of deciding what your delta is and all that kind of stuff. Okay, so proof. Let me write explicitly what, by the way, I'm going to ignore the index n here because I don't want to write it all the time, so I will just write phi. So let me write st of phi x again for you because I need to make a couple of change of variables. So this is the sum in k in ZD, and then I have phi k, and then I have explicitly e to the I x k1 x1 or k1 of t1. So the t1, t2, td are the periods here. This is just n general torus, so plus 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 xd kd td. And then there is e to the I t, what I call k star square. That one has the over t's in there. So k star square is the sum in k of ki square over, I, ki square ti square. And the t's are the periods. Okay. Now we know that this k star is less or equal than n, up to constant, because that comes from the support of the phi. Okay. First change of variable, we're going to call eta I to be ki over tin. And a eta is going to be for me the definition of phi. So I'm trying to set up so that I can use the corollary that I had before. Phi hat, okay, n. And now I change variable, so this is ni tin. Because my k, which was what was in here, is now ni ki, you know, okay, it's change of variable. So here it should be the vector xi. But the vector xi, vector k, right? That's here, this guy, this k. But k is now changed into eta times tn. Okay, so I'm just reporting that. Okay. Now, I'm integrating td cross I, that's my left-hand side there, st phi n q dx dt. Then I have to take the Q root, but let's just like that. OK, so this is the same as taking the integral Td cross I dx dt of the sum eta. But remember now, this eta, these guys are discrete, right? And they are in the parabola. Anyway, eta of A eta, but that's this guy, depends on phi. And then e to the I of x1 eta 1 n plus plus xd eta d n, and then minus, minus or plus? I guess it was plus. Doesn't matter. There is an I anyway in front. So plus t of n square eta square, and then all of the thing q. I just wrote it down with the new coordinates, change of variables. Now set, so first I did a change of variable in the frequency space. Now I'm going to do in the special variable. So I'm going to call xin to be yi, I from 1 to d. And then yd plus 1 to be, so this is a change of variable. So this is going to be the last one, which is t n square. This. No, I don't need to put this guy. Yeah, there we go. OK. Now the Jacobian. So I'm going to do this change of variable here, dx dt. So there is a Jacobian, and the Jacobian is 1 over n d plus 2. Because from here, now my dx is 1 over n, and I have that d times, and dt is 1 over n square. So that's that. OK. We note that the yi are less or equal than n from there, because the x were in the torus, up to constant, of course. Maybe the constant of the period, that's not important here. And the yd plus 1 is less or equal than n squared, the length of the interval. OK. So continue up there with my change of variable. This is going to be 1 over n d plus 2. That's the Jacobian. And then I have the integral in y I less or equal than n. And the last one, d plus 1, less or equal than n square I. And when I write everything down, this is the sum of eta and eta e to the I of the vector y, the vector eta. I'm sorry, it's a bit of notation. The vector y is just the first d of them. So here my notation is that the vector y is y1, yd. OK, that's the first piece. And then plus the y d plus 1 eta square. And then this is q. And then dx, dy, dy plus d plus 1. OK. All right. We'll agree on this. So now you see that you are in the parabola. This is what I was saying before, that here you don't quite recognize that you are in the parabola, but you are, and this is written explicitly. So we are almost OK in using this, except what do we have to fix?
What about the lambda, capital lambda?
The capital lambda is this where the eta is, And if you look at where the eta are, those are discrete points because it depends on the k, except they have been adjusted. So we need to do two things. We need to decide what's the delta that separates these points on this lattice. But another thing is important. This is not a ball in RD plus 1. So we are in this dimension. So this is RD. This is the next coordinate. So in this dimension, we are in minus n, n. But in this dimension, we are much bigger. And we need to make sure that we actually do have a ball here, or a rectangle, or whatever, but it has to be, a ball. But that's easy to fix, because let's remember that in this direction, this is the x variable, which is periodic. So in that direction, we are periodic in RD. We're still in x. We're still in the torus. So what you can do is you can make this direction as large as this one, except that you have to divide by that many times you're doing this. So we can adjust and have here the ball or radius n square I. Of course, we have to divide by how many times we do that. So this is the same by periodicity. So how many times? So if we are in one dimension, this is of size n divided by this, this thing divided by the number n. So how many times will be n square I divided by n? So we have to multiply n I times in order to be in the right thing. So we have to multiply by that, and we have to divide by it to be consistent. So it's 1 over n d plus 2 divided by n I. And now here, this can go all the way to that. So it's y less or equal to n square I. And the last one, now this is the ball. Now, this is a cube, but anyway, this is included in the ball or radius r, where r for us now is of the order, if you want, n square I. And here's the same thing. We didn't change anything. We just used periodicity, the fact that it's periodic in this direction to stay inside the ball, as this theorem tells us.
So
We still,
there does not depend on R, which is
yes,
But you're normalizing.
we are normalizing here,
R in
which we didn't do it yet. We have to do that. We didn't do. I'm going to do in the next step. All right, and we had to figure out what's the delta. Exactly. Good. Oh, delta, OK. It has to be delta 1/2. OK, so let's see now. So we're getting closer and closer. OK, I think I didn't miss anything. So now the set for us, the set delta, what is this? This is eta 1 all the way to eta d. And then, of course, the last one is the square of all of this, because we are in the parabola, is delta 1/2 separated with delta 1 over n squared, as was guessed. And r, which we just looked what it is bigger than, remember, this is of the order n square I, and this is bigger than delta to the -1. OK. So we are basically all set to use what is hidden down below here, which is this. Except the last thing we have to do is we have to divide, because we didn't do the average yet. So I'm going to do that in the next step. OK, so keeping track of all the n's. This is the Jacobian, d plus 2. I'm almost done. Huh? I will not take you more time than n, this was from periodizing. We have to divide, multiply by the measure of the ball. So that's the radius is n square I, and the dimension is d plus 1. And divide by it. So now this. And then the ball r. And then the expression that you have there, and then this is the power q, dx dt. And now here we can use just that we have down below. We know exactly what delta is. So at the end of the day, I can tell you that this is less or equal to what we want. OK, I don't think I need to. Of course, it is to the power q. You had to take 1 over q of this, but that's the end. And sorry, 5 more minutes.
So
you guys have this. If you leave,
theorem sharp?
the decoupling theorem is sharp, correct? The decoupling theorem it is, as far as I know.
Okay. Does it work for other configuration, like for example?
Yes, there is an equivalent for cone.
For cones, yeah.
There is an equivalent for. So you need to understand. You need to have curvature, except in the cone, of course, there's a point. But there are variations of that, and that's been used in all sorts of different things, and that's been used to prove theorems in number theory actually now, because this connection between the Diophantine solution of Diophantine equations and stuff here. Thank you. Thanks, guys. So if you want my notes, send me an email. Or maybe, I don't know, should I send it to somebody? There's a place where I can put it. I don't know. You let me know. But maybe you're fine. You don't need that. But, or email me. I'll send it to you. It's not.
Okay. Very, very nice. Yeah. So I didn't.
You see?
Yeah, I didn't know these things.
You learned something.
Absolutely.
I wanted
Yeah.
to listen to Lily.
Oh, yes, definitely. Is your student, Lily?
No, postdoc.
Postdoc. Wow, she's too young. So after you are older or a certain age, and then everybody looks just a student. Sorry, I don't want to shake hands because I'm all full of. You are at the IS.
Yes.
Very good, very good. Excellent.
Shall I go to lunch?
Yeah, I mean, if you're going.
Lily, you want to go?
Yes.
Okay.
The Sobolev endpoint is true, I think.
Sobolev point.
Like, because you're just using.
Without the epsilon, you mean?
Like there was this question of it, like if you need S strictly bigger.
Yes.
And I think all you need to do is you need to use a little K square function estimate.
And they will be,
Right.
and the epsilon, you don't.
Because like you would have LQ and like PX,
Yeah.
which is comparable to ST PN phi, LTXQ, and little l in the dielectric frequency
Yes.
by the little K square function.
Yes.
But then the Q is bigger than 2.